Hello and welcome. Did you hear about the man who is determined to count back all the way from 1,000,000? He says he'll stop at nothing. In this video, we're going to get a taste of differential equations, which is a topic of a whole other class. In fact, many of you might be taking that class down the road. But here, we're just going to get a taste of it. This covers 9.1 and 9.3 in a single packet. Let's get started. A car just drove by, you probably heard it. So a differential equation is an equation that contains an unknown function and some of its derivatives. So below are some examples of differential equations. We have the second derivative of y with respect to t equals g, where g represents that constant 9.8 meters per second squared. And what this is an equation, a differential equation, that models the distance that an object has fallen. So it says that the second derivative of the y function, which represents the distance that the object has fallen, so the second derivative would be acceleration, right? That is a constant. That is a constant. So that models that object that's falling. The second differential equation is a model for something that's falling that has a parachute. So here the function in question is velocity. So it models what the velocity of that object is as it's falling. You can see on the left side here we have mv prime. If you remember, F equals ma. Another way of writing a is the derivative of velocity. So you can see right here on the left side we have basically F equals ma. And then on the right side you have a couple of terms that you have the mg term, which is, if there was no air friction, then that would model how fast the object is falling. But then you have this minus bv squared, which models the effect of the parachute. So it's a force that's going in the opposite direction as it catches the air. The third equation, differential equation, is modeling a pendulum swinging back and forth. So that little picture is drawn off to the right here. And the function here is theta as a function of time, where theta represents the angle from this dotted line to the pendulum. So that's going to be changing over time as the pendulum swings back and forth. And this is the equation then that models what that function is over time. Some other examples are population growth. So the equation here is dp dt equals kp. Here, the idea is that the more people there are, the higher the birth rate. And that's what the equation is modeling. The more people there are, the higher the population p, the higher the rate at which the population is going to change. That makes intuitive sense, and it's captured by this differential equation. Now what you could do is you could solve this differential equation, and that's one of the techniques we're going to learn in this section, is how to solve a differential equation like this. And then the function that you get for p of t is what is then going to model population growth over time. So solving a differential equation like this involves finding that function that satisfies the differential equation. The last example is the motion of a spring. So we have m times the second derivative of x with respect to t equals negative kx. This is actually the differential equation version of Hooke's law. Hooke's law was F equals kx. Remember, that modeled the force that the spring acts on an object, where x is the distance away from its natural length. Here you'll notice that there's a negative kx instead of a kx. So we're taking x to be signed in this differential equation, whereas in Hooke's law we were not taking x to be signed, positive or negative or anything like that. It was always positive. And you might notice that F, the force, can be represented as ma, where a is the acceleration of the object on the spring. But a, the acceleration, is the second derivative of the position. So that's what we're seeing right here. We're seeing m times a, where a is written as the second derivative of the position. That way we have this differential equation where x of t, the position function, is the unknown function. So we can try to solve this differential equation and try to figure out what an equation, what a function would be, x of t, that models the position of the object on the spring. Now, not too surprisingly, if you do solve this differential equation, you're going to end up with some kind of oscillating function, like a sine or a cosine. We're not going to solve this type of differential equation in this class, but in future classes, when you take a differential equations class, you definitely look at that. Now, differential equations are abbreviated DEs. You might hear, I'm taking DEs. That just means I'm taking the class studying differential equations. A solution to a differential equation, to a DE, is a function. So all throughout these examples, we've mentioned that the solution to the equation is a function. So in the first case, it was y of t would be the solution to this equation. The second example, v of t would be the solution, and then theta of t, and then p of t, and then x of t. So it's a little bit different than the equations that we've seen so far, where the variables are the unknowns, and those are the solutions. You know, x equals 5 is a solution to a typical equation, like a regular equation that you've seen before in algebra. But for differential equations, the solutions are functions. That's the key shift. One more bit of vocabulary is that the order of a differential equation is the highest derivative that appears in the equation. So running through our examples, the highest derivative we see in the first example is a second derivative, so that's order 2. The highest derivative we see in the second equation, or second example, is a first derivative, so that's order 1. And then third example, what do you think that would be? Second order, because a second derivative. What about the fourth example, population growth? That would be first order, because we see a first derivative. That's the highest derivative we see. And the last one? Second order, because that has a second derivative. Let's get a little bit of practice in example 1, showing that a function is a solution to a differential equation. So we have in example 1 this differential equation y prime equals y over x. Y prime minus y over x equals 2x cosine 2x. So that's a differential equation that can have some kind of solution. And here we have a proposed solution. Y equals x sine 2x is this proposed solution to this differential equation. Now we're not saying how we got this proposed solution, we're just being proposed the solution. But what we're going to do in example 1 is show that that proposed solution actually is a solution to this differential equation that we're given. So what we can do is first, let's see, looking at our differential equation, we're going to need y prime. In fact, what we'll do is we'll say the left-hand side is y prime minus y over x. So we're going to need y prime. Now y prime involves a product rule, right? If we take the derivative of y with respect to x, we're going to have to use a product rule. So let's do that here. We have first times the derivative of the second, so the derivative of sine 2x would be cosine 2x times 2 by the chain rule. Then we have plus the derivative of the first, derivative of x is 1, times the second, times sine x. So that's the product rule for this function, x sine 2x. Then we have a minus y over x. Now y is x sine 2x. And then we have an x in the bottom as well. So what we have here is 2x cosine 2x, and then we have plus sine 2x minus, then if you notice, the fraction here has x's that cancel. So an x cancels from the x sine 2x and the x on the bottom. So we just get minus sine 2x. And now the sine 2x's cancel. Just try to simplify this as much as we can. So we just get 2x cosine 2x. Then if you notice, the right-hand side is 2x cosine 2x, which is exactly what the left-hand side turned into. So the left-hand side is equal to the right-hand side, is equal to, let's say, 2x cosine 2x, which is equal to the right-hand side. In other words, taking this proposed solution and plugging it into the differential equation like we did, you get that the two sides are equal. So we did have a solution. The proposed solution actually was a solution because it made the equation true. It made both sides of the equation equal to each other. This is just like when you try to prove a trig identity, right? You either start from the left-hand side, work your way over to the right-hand side, or start with the right-hand side, work your way over to the left-hand side, or you can just take the left-hand side, simplify it, take the right-hand side, simplify it, and then show that the two sides are equal to each other. That's the kind of method that we used here, just in case the right-hand side ended up being a little bit more complicated. Here we could have just at the end said, this last step of the left-hand side, you could say, oh, that's just equal to the right-hand side, and then box your answer. But I'm just showing you how to write it up in general, just in case the right-hand side ended up being a little bit more complicated and you had to simplify something. So for example 2, it says, show that each member of the family of functions y equals c e to the 3x is a solution to the following differential equation, y prime equals 3y. So once again, we're asked to show that we have a solution here. So on the left-hand side, we've got y prime. And if we look at y prime, let's see, c e to the 3x. C here is just a constant. Usually that you can take that to just be a constant. And then 3 is a constant as well. I don't know why I mentioned that, but there you go. So when we take the derivative, that constant coefficient will hang around. And then when we take the derivative of e to the 3x, that's going to be e to the 3x times the derivative of the inside, so times 3. So we'll just get 3c e to the 3x. Oops. So that's the left-hand side. Then we have the right-hand side is 3y, which is 3 times, and then replacing y with c e to the 3x. You just get 3c e to the 3x. So these two are equal. All right, so we'll just leave it at that. My box blue for no reason. We showed that the left-hand side and the right-hand side are equal. Now, the general solution to a differential equation is a family of solutions. And example 2 shows an example of a general solution. Y equals c e to the 3x is a general solution because no matter what c is, we still have a solution. Y equals c e to the 3x is still a solution to this differential equation. So y equals c e to the 3x you can take to be not just a single solution because c can be anything, it's actually a whole family of solutions. You could write y equals 2e to the 3x and it would be a solution. You could write y equals 5e to the 3x and it would be a solution to the differential equation. So it's a whole family of solutions. It's an infinitely large family. You thought your family was large, right? Now if we're given an initial condition, for example y of 0 equals 4, well, that's going to pull out a particular member of the family. It's going to be the one that solves y of 0 equals 4. In addition to solving the differential equation, it'll solve y of 0 equals 4. And that would be called a particular solution of both the differential equation and the initial condition. The initial condition, again, being this y of 0 equals 4, or something similar to that. It's called an initial condition because a lot of times these functions are functions of time, and a lot of times time will be started at 0 for these functions, so t equals 0 would be the initial condition. And so a lot of times you'll be given these as your function with t equals 0 plugged in equals something. So if that function represented, for example, the height of an object, right? This could say that at the beginning of time, at the start of time, being measured at least, not going all the way back to Big Bang or something like that. So at the beginning of when time is being measured here, the height of the object is 4. So that's the initial condition. You know, it could be a different initial condition. Maybe the height starts at 10, and then your function would look a little bit different. So that's initial condition, and the combination of a differential equation and an initial condition is called an initial value problem. Sometimes that's abbreviated IVP. I'll write that in here. IVP. So as an example, y prime equals 3y, the differential equation we were looking at in example 2, and then paired with y of 0 equals 4 would form an initial value problem. So it's a DE plus an initial condition makes an initial value problem. Now y equals 4e to the 3x happens to be the particular solution to that initial value problem because it's a solution of both the differential equation and the initial condition. So whereas y equals ce to the 3x was a general solution of the differential equation, y equals 4e to the 3x was a particular solution of the initial value problem y prime equals 3y and y of 0 equals 4. Okay, let's check something here. Alright, so that's probably good for this video. Thanks for watching, and see you in the next part.